Hey everybody. Oops, let me do that. We'll get started in a couple minutes here. Hopefully you all got the note about class. I mean, obviously if you're here virtually, you might have gotten the note, or you might have just planned on coming virtually anyway. But class is meeting virtually today. We are expecting protesters, although I just looked outside and there isn't really anyone out there. So yeah. And I was going to, let's see here. I'm going to pin my video here. And I'm going to do that. Yeah, let me grab this. Cool. So let me grab the chat as well. So here's a link to the attendance form as usual. Please do fill it out when you have a second. Also, I'm going to make the chat, I guess private's not the word I'm looking for. I'm going to make the chat so you can only chat with me, so that if you have a question, you're welcome to ask it via chat and no one else will see it. So I believe I did that. Yeah. So please feel free to ask questions. In the chat. Only I will see the questions. It's 9:59. We'll get started soon. Let me get my camera set up here so you can see things. I'm planning on covering the practice problems for midterm 2. We probably won't get through all of them because there's quite a few graphing ones. So I'm going to actually skip the graphing ones and save them for last and go over all the other stuff first. That said, if there's something specific that anyone would like me to cover, I'm more than happy to do that. Just let me know. You can either unmute yourself and say words, or you can do the other thing where you don't unmute yourself and you type in the chat instead. So yeah, just so everyone knows, right, we're going over practice problems for midterm 2. You can certainly find this handout in Canvas if you want to follow along with it. You certainly don't need to, though. I'm going to write stuff down. So let's go ahead and get started. And my pens are still sucking, so I'll do my best here to write with them. I guess I can just write in red. My red pens all work, so I never use them. So let's go ahead and start with this first question here. I want to simplify the difference quotient. Let me move my paper around here. Cool. So we want to simplify f of x plus h minus f of x over h for the following functions. So for 1a, the function is f of x equal to 3x plus 7. And I think it's worthwhile, instead of just writing all this out from the get-go, though you certainly can, you might first want to write out that f of x plus h is just 3 times x plus h plus 7. And then we can use those two pieces to write what this is. So then our difference quotient, f of x plus h minus f of x all over h, is going to equal, well, there's f of x plus h, 3 times x plus h plus 7, minus f of x, which is 3x plus 7. We do want parentheses around that, all over h. And then your job after you write this expression is to simplify as much as possible, specifically meaning you want to make sure that you cancel out this h in the bottom at some point. It's not going to happen right away, right? You have to do the algebra to make that happen, but that is the ultimate end kind of goal, is to make sure that that h right there gets canceled. So let's see here. Let me like that. My shade here is getting some weird sunlight from my window here. So let's see, I'm going to distribute. I'm going to get 3x plus 3h plus 7, distribute here as well, minus 3x minus 7 all over h. 3x minus 3x is 0. 7 minus 7 is 0. So we're left with 3h divided by h, which is just 3. So that would be our answer here. For the other function, it's a little bit more work. So for the second one, the function is 2x squared minus 3x plus 9. And if I'm going to write down f of x plus h as well, f of x plus h, again, I'm just taking every x and thinking of it as a parentheses instead. So 2 times parentheses squared minus 3 times parentheses plus 9. And I'm filling in the parentheses with whatever's in the parentheses, in this case, x plus h. So then I'm going to write out what f of x plus h minus f of x all over h is. I'm going to get, let's see, f of x plus h is 2 times x plus h squared minus 3 times x plus h plus 9 minus 2x squared minus 3x plus 9 all over h. I do expect to see work for these problems, right? Don't just jump to the answer. We want to show our work. So I'm going to get 2 times, let's see, x plus h squared is x squared plus 2xh plus h squared. Distribute the minus 3, you get minus 3x minus 3h plus 9. Distribute the minus sign, you get minus 2x squared plus 3x minus 9 all over h. Let's say I can cancel some stuff at this point. I can cancel a minus 3x and a plus 3x and a plus 9 and a minus 9. I can't quite cancel out the negative 2x squared yet, though, because I have to distribute this 2 before I can do that. So I'm going to get, let's see, 2x squared plus 4xh plus 2h squared minus 3h minus 2x squared all over h. Then 2x squared and the negative 2x squared do cancel out. They out to 0. And then we end up getting 4xh plus 2h squared minus 3h all over h. I like to factor out an h here, but you can also just divide each thing by h. It's the same idea. If I factor out an h, I'm left with a 4x plus a 2h to the first minus 3, all divided by h, and then these h's cancel to leave us with a 4x plus 2h minus 3. For those of you that are joining us, we're just getting started with the practice problems for midterm 2 review. Here's the attendance form, in case you need it. Please do fill it out when you have a second. So we're going to skip question 2 for now, and we'll come back to do it and do as much of the graphing as we can at the end. But let's go ahead and move on to question 3. Also, again, if you have questions, you're certainly welcome to ask them. So question 3 says the following. If f of x equals x plus 2 divided by 2, and g of x is equal to 3x minus 4, find the following. F of g of 4. And if I'm finding these, I typically encourage you to work from the inside out, meaning I want to find g of 4 first. So first, g of 4 is equal to 3 times 4 minus 4. Whoops, there's no parentheses there, sorry, which is 12 minus 4, which is 8. And then f of g of 4 is going to be f of 8, which is going to be 8 plus 2 over 2, which is 10 over 2, which is 5. For part B, same idea. If I'm going to find g of f of 4, then I'm going to find f of 4 first. So f of 4 is 4 plus 2 over 2, which is 6 over 2, which is 3. So then g of f of 4 is equal to g of 3, which is 3 times 3 minus 4, which is 9 minus 4, which is 5. And I would say it is a coincidence here that g of f of 4 and f of g of 4 both equal the same thing. These are not inverse functions. They are not necessarily going to give you the same result when you go one way or the other. But so it is purely coincidental that they happen to be the same value. So we're going to find f of 4. Now this is a good time to kind of observe where you don't need to redo the work you've already done, right? We already found f of 4 in one of the previous 2 problems, so we might as well just use that already. So let's see, f of 4 right here was 3. So I know that this is going to equal f of 3 because f of 4 is equal to 3. And then f of 3, well, f of x is x plus 2 over 2. So f of 3 is 3 plus 2 over 2. which is 5/2. And you can either leave it as 5/2, or if you prefer to get a decimal since it's an exact, you can find that to be 2.5. I would generally encourage you to leave your answers as fractions. Part D, find f of g of x. So unlike the previous 3 parts where you had a number in the argument of your composition, for this last one, we have a variable, meaning our answer is going to be just a function that is the composition of these 2 functions. So we're still going to work from the inside out. We're going to do f of g of x is 3x minus 4. And we know that f of x is x plus 2 over 2. So f of some stuff is our stuff plus 2 over 2. And we should simplify this. So this is going to be 3x minus 4 plus 2 is minus 2 all over 2. And that's about as simple as it gets. You could divide each part by 2 if you really wanted to and say it's 3/2 x minus 1. But I don't think that's particularly necessary here. Okay. Again, you're welcome to ask questions if you got them. If you don't, I'm just going to keep moving on. All right. Also, I'll post these notes later, of course, as well, if you want to look back at them. I believe the solutions to this are already posted, though, so you can also look there. Let's look at problem 4. So problem 4 is a graphing problem, but it feels like it's worthwhile. So let's see, graph indicating all important features, vertices, intercepts, asymptotes, etc. So the first one is f of x equal to e to the x when x is less than or equal to 0. And the absolute value of x minus 2 when x is greater than 0. Here's that attendance form. I'm just going to, whenever someone new comes in, I'm going to keep giving the attendance form so that you can use it. Of course, I know it's available in other places, but there you go. So let's see, graphing this, you certainly don't have to graph all the individual pieces like wholly, but you can, right? Like I can do a quick little graph of e to the x. Here's e to the x. And a quick graph of the absolute value of x minus 2. That's going to be the usual absolute value graph shifted 2 to the right. So it'll look like that. There's my e to the x and my absolute value of x minus 2. And then I know for e to the x, I want x to be less than or equal to 0. So I want this part of it to the left. That's the part I actually want. I don't want any of that part to the right. Similarly, for the absolute value of x minus 2, I want everything when x is bigger than 0. So I want everything to the right of that point there. So I want all of this. So those are the 2 pieces I'm going to put together on my graph. So my actual graph is going to look like the following. It's going to be e to the x to the left. We are going to get that y-intercept there, which we'll talk about in a second. And then, so I should probably, before I continue on, I should think about what my points are going to be. So that point there that I'm getting is the point 0, 1. So we plug in 0 for x, e to the 0 is 1. This point here that I'm not quite getting, but I'm going to have a hole at, is going to be, well, if x is 0, the absolute value of 0 minus 2 is positive 2. So that point up there is going to be that right there, which is an open circle. And then I have this x-intercept of positive 2. It's going to look like this. Definitely when you're drawing a piecewise function, you should include any endpoint where one piece ends and another piece begins. So I should definitely label this or somehow indicate that I know that that's going to be 0, 1. And even though this 0, 2 isn't actually technically a part of the graph, we're still going to label it. So that 0, 2 is also important to make sure that the reader knows what it is. And then you should also label the x-intercept here. 2, 0. Cool. All right, let's look at question 4b. That was 4a. Let's look at 4b. Also a piecewise function. So we're going to have the following. F of x is equal to x squared when x is less than or equal to 0. The natural log of x when x is between 0 and 1. Specifically greater than 0 and less than or equal to 1. And 1 minus x when x is greater than 1. Well, it's written the other way in the problem, but same deal. So again, you don't need to plot all the individual graphs separately if you don't want to. I like to just so I can see it, but you can totally skip to just the result at the end. But in fact, actually, let me do it that way first, and then I'll kind of backtrack to show you all the individual graphs. But if I was just trying to graph this all in one shot, here's what I would do. So, okay, well, I know what x squared looks like. I only want x squared up to x equal to 0. So I want x squared to the left. So I'm going to get the point like 0, 0, and negative 1, 1, and negative 2, 4. If you want to plot those points, I don't really want to plot them. I just want to kind of get that there. It comes in like that. And I do get that point at 0, 0. And then for the natural log graph, natural log of x, I know I have a vertical asymptote for the natural log of x at x equal to 0, and it has an intercept at 1, 0. So the natural log graph that I'm going to get is going to be this piece here, and it's going to stop right there. That's all I get for the natural log graph. Right? It would continue on that way, but I'm stopping at x equal to 1. And then lastly, I have the graph of 1 minus x, which is a straight line. It would have a y-intercept of 1 and an x-intercept of 1, but I'm going to start here. So it would come down like this, kind of watch. It would come down like this, but I'm going to start it right there. So I would have had an open circle there, but since it's already filled in, it's filled in. And then it's just going to continue like that. Sorry, this pen is dying. So that's how you could certainly do the graph by just kind of graphing all the pieces. We should label again, we should label this point here as 1, 0. We should label this point here as 0, 0. And we should point out, or we should somewhere write that there is a vertical asymptote at x equal to 0. Vertical asymptotes or asymptotes on the axes, you kind of need to extra indicate because, right, you can't really draw the asymptote there as the line's already kind of filled in. But for any other asymptote, you should draw it as a dashed line. If you wanted to show all the pieces, right, you can be like, okay, I know x squared looks like a parabola, and I just want everything to the left. So I want all this. And I know that natural log of x looks like this. And stop, and it has an intercept at 1, 0. I just want all of this. And then finally, 1 minus x would have a y-intercept at 1 and an x-intercept at 1 and would look like this. But I just want everything from here moving forward. So that's how you could think of all the little pieces you would need to graph this piecewise function if you didn't just see it kind of from the get-go. There's the link to the attendance form again. If you're just joining us, please do fill it out. You've already filled it out, great. Let's move on to question 5. Try and keep things in order here. Okay. So question 5 is finding the domain of the following functions. I'll remind you all, there's 3 things to think of when you think about domain, either possibly division by 0, having a square root, or having a logarithm. Those are the 3 things we need to look for. So with this first function, for f of x equal to the square root of x to the 6th minus 7x to the 5th plus 10x to the 4th, we need all of that stuff inside the square root to be non-negative. So we're going to set the insides to be greater than or equal to 0. Usually when you're solving something greater than 0 or greater than or equal to 0, factoring is the best way to do this. So I'm going to factor as much as possible. So when I factor, there are kind of 2 things I do when I factor. First, I look for, is there some greatest common factor I can pull out from every piece? And in this case, yes, there is. There's an x to the 4th. So I can factor out an x to the 4th. I'm left with an x squared minus 7x plus 10. Still greater than or equal to 0. And then I ask to solve for the remaining pieces. Is there any other factoring I can do? Well, yeah, this one factors in kind of the typical way. I can have a factor, sorry. It factors as x minus 5 times x minus 2. And then typically what we do is we use the number line. And we plug in all the places that make it equal to 0 or undefined. Yeah, that's a good question. So someone asked, do you always, in fact, we're going to see the answer to your question. The next part is, so I would say if you have a square root or a fourth root or any even root, you're always setting the insides to be greater than or equal to 0, because it's totally fine to take the square root of 0, right? Square root of 0 is equal to 0, because 0 times 0 equals 0. On the other hand, if you have a logarithmic function, we set the insides or the argument to be strictly greater than 0, because we can't take a log of 0. So that's going to be the difference. And we'll see that in just a second here with the next example. Good question. Thank you for asking that. So on here, I'm going to have 0 and 2 and 5, because those are the numbers that make each of these parts equal to 0. And we know we want to include those numbers because 0 makes this whole thing equal to 0. And 2 makes the whole thing equal to 0, and 5 makes the whole thing equal to 0. So I'm going to include all those points. And then I'm just going to test points in between each of these, I should say, test points in each of these 1, 2, 3, 4 intervals to see if the overall sign is positive or negative. So if I plug in something like x equal to 6, 6 to the 4th is positive, 6 minus 5 is positive, 6 minus 2 is positive, and a positive multiplied together is going to be positive. You're always testing a point that's not one of the endpoints. If we plugged in 5, you would just get 0. And in here, I'm going to test, I don't know, x equal to 3. 3 to the 4th is positive. 3 minus 5 is negative. 3 minus 2 is positive. And a positive times a negative times a positive is negative. And then we're going to test something like x equal to 1. So I plug in 1. 1 to the 4th is positive. 1 minus 5 is negative. 1 minus 2 is negative. Positive times a negative is positive. And finally, plug in something less than 0, like negative 2. Negative 2 to the 4th is positive. Negative 2 minus 5 is negative. Negative 2 minus 2 is negative. And a positive times a negative is positive. Another way to think about this, which you may have seen before, is that this 5 came from this factor with an odd power, so the sign changed. This 2 came from a factor with an odd power, so the sign changed. The 0 came from a factor with an even power, so the sign stayed the same. And that is something that's always true. If the powers are odd, the sign's going to change at those zeros. If the powers are even, the sign's going to stay the same at those zeros. In any event, we want this, we want this, we want this. So we really want all of this. That's our domain. We do want to write an interval notation. So, and I should point out, there shouldn't be any stopping at 0, right? We go all the way from negative infinity straight through to 2. Even though 0 was an important point to consider, we don't have to stop there. So the correct way to write this domain is everything from negative infinity to 2 inclusive union 5 inclusive to infinity. We have parentheses on infinities because we never include infinity because it's not a real number. And we have brackets on 2 and 5 because we want to include the values of 2 and 5. And so we use a bracket to indicate that. Okay, let's look at 5b. For 5b, which is the function f of x equal to the log of 4 minus x squared. Quick question, what's my base? Yeah. Yeah, good job. All right, thank you, everybody. That's excellent. So the base is 10. Not that we need to know that here, right? The base doesn't have any effect really on what the domain is going to be, but it's still good to know. So for the domain here, we're going to set the insides to be strictly greater than 0. We don't want them to equal 0. We're still going to approach this the same sort of way. We're just going to get a slightly different result. So although you could bring x squared to the other side and square root both sides, I really can't recommend enough factoring. We should factor this as 2 minus x times 2 plus x. The reason we should factor is because if you do it the other way, and if you do it the other way, you will get x equal to plus or minus 2, but it's harder to see where it's going to be positive and where it's going to be negative. So I really recommend factoring it. Then on our number line, we're going to get x equal to positive 2 and x equal to negative 2. And we're going to do the same thing we did before. We're going to pick a number over here, like 3, and plug it in. 2 minus 3 is negative, 2 plus 3 is positive, and the negative times the positive is negative. And plugging in x equal to 3. If we plug in something like 0, 2 minus 0 is positive, 2 plus 0 is positive, positive times positive is positive. And then finally, if we plug in something like x equal to -5, 2 minus -5 is positive 7. 2 plus -5 is -3, and positive times a negative is negative overall. We don't want the endpoints, so we use open circles to indicate that, although it's perfectly fine if you don't draw anything there specifically. And we only want the places where it's positive. So all we want is everything between -2 and 2. I don't want anything bigger than 2. I don't want anything smaller than -2. So my domain here is going to be -2 to 2, and that's it. So just to kind of go further with this a little bit, like if x were equal to 3, for example, 3 squared is 9, and 4 minus 9 is -5, and we can't take the logarithm of -5. In a similar way, if x were -5, -5 squared is 25, and 4 minus 25 is -21, and we can't take the logarithm of -21. But if x were equal to 1, 4 minus 1 squared is 3, and log of 3 is something we can find. It's not a nice number, but it is a real number. Similarly, if x was like 1.99, 1.99 squared is almost 4. So you'd have 4 minus something very close to 4, like a very small number. And then you could still take the logarithm of a very small number. So that's why this is our domain. You can get anything between -2 and 2, but nothing outside of that. All right. Let's look at problem 7. Sorry, problem 6. Apologies. Problem 6. So problem 6, let's see here. We've got finding the inverse of some stuff. So 7a, we want to find the inverse of f of x equal to 7x minus 2 over 9. And so I do recommend following the usual process for this, meaning you're going to write y equal to 7x minus 2 over 9. It's totally fine if you skip this first step and just jump straight to interchanging x and y and saying x equal to 7y minus 2 over 9. And then we're going to solve for y. Oh, that is 6. Yeah, sorry. I even said 6 and then I wrote 7. Good call. Thanks. That is 6a. Good call. So then you can multiply both sides by 9. Add 2 to both sides. And, excuse me, divide both sides by 7. And then you should probably write that your f inverse of x is equal to 9x plus 2 over 7. It's probably not a huge deal if you don't do this, but it looks nicer. So that's the idea. You switch x and y, you solve for y. Sometimes it's easy, sometimes it's a little bit harder. Let's look at the next example, 6b. And it's 6b, yes. So let's see what I have here. I've got f of x equal to the log base 2 of x plus 1 minus 3. Same deal. We're going to first write it as y equal to log base 2 of x plus 1 minus 3. And then actually, I will point out that these next two steps are kind of interchangeable. Some people do like to just take this and solve for x first. And then after they solve for x, interchange x and y. I prefer, probably because I learned it that way, to first interchange x and y and then solve for y. But either way is really fine. So we got x equal to log base 2 of y plus 1 minus 3. And now we're going to try and solve for or isolate y. So first I need to add 3 to both sides. So x plus 3 equals log base 2 of y plus 1. And then rewrite this as an exponential equation. So instead of log base 2 of y plus 1 equals x plus 3, I'm going to have base 2 raised to the x plus 3 power equal to y plus 1. Finally, subtract 1 from both sides and get 2 to the x plus 3 power minus 1 equal to y. So here my inverse function is going to be 2 to the x plus 3 minus 1. Sure. 6c. My function here is 1 over x to the 5th plus 4. So once again, we write it as y equal to 1 over x to the 5th plus 4. We interchange x and y, so get x equal to 1 over y to the 5th plus 4. And then we start solving for y. There's a couple ways to do this. I would, yeah, and really kind of whatever you like is fine. You could either start by multiplying everything by y to the 5th, or you could start by subtracting 4 from both sides. I would probably subtract 4 from both sides first, although either way is fine. Now, something you can do that's kind of a shortcut, which is totally fine, is from this step, you can just take the reciprocal of both sides. So I'm going to show you the work, but the end result is going to be that 1 over x minus 4 is equal to y to the 5th over 1. The intermediate step is to multiply both sides by y to the 5th. So multiply both sides by y to the 5th, I get y to the 5th times x minus 4 equal to 1. And if I divide both sides by x minus 4, I get 1 over x minus 4 equal to y to the 5th. So it's totally fine to do this intermediate step, but it's also totally fine to just take the reciprocal of both sides if you want. And again, we're doing that because we're trying to isolate y, so we want y out of the denominator. Lastly, we're going to take the 5th root of both sides. So y is going to equal the 5th root of 1 over x minus 4. Or if you prefer, you could write it as 1 over x minus 4 raised to the 1/5 power. Either way is fine. So finally, our inverse function here, f inverse of x, is the 5th root of 1 over x minus 4. Or if you prefer, it is 1 over x minus 4 raised to the 1/5 power. Same thing, just written a different way. All right, I'm just going to keep going. Definitely stop me or write something in the chat if you have questions. Here is the attendance form again, just in case anyone hasn't gotten it. So let's look at 7. For real this time. Come on. 7. Determine if the function is even, odd, or neither. Be sure to use the techniques discussed in class. So definitely for showing a function even, odd, or neither, I do expect to see the following sort of work. So for f of x, and this is 7a, for f of x equal to 3x to the 4th minus 2x squared, you might know it's already even because it's a polynomial where all the powers are even. And even if you already know it, you still need to show the work so that I can see that you know it. So you can't just write that it's even. You just say it's even, you might get like half a point. So the way we show it's even is by starting with f of negative x. And we get 3 times negative x to the 4th minus 2 times negative x squared. And then we simplify. So negative x times negative x times negative x times negative x is positive x to the 4th. And negative x times negative x is positive x squared. But this is exactly the same as the function we started with, which shows that the function is even. Because we've shown that f of negative x is equal to f of x. You don't actually have to write that part there, but you need to get from seeing that f of negative x is equal to f of x. Okay, let's look at 7b. F of x is equal to x cubed over x to the 6 plus x squared plus 1. So typically the flow chart for doing this kind of problem is first to check if it's even. So first I'm going to ask myself, is it even? Meaning, is f of negative x equal to f of x? I'm going to start that by finding f of negative x. So f of negative x is equal to negative x quantity cubed over negative x to the 6th plus negative x squared plus 1. And the thing that always happens with these kinds of problems is if you have a negative x to an odd power, you're going to keep the negative sign because it's a negative times a negative times a negative, which is negative. And if you have negative x to an even power, you're going to lose the negative sign. So negative x to the 6th is going to be positive x to the 6th, and the negative x squared is going to be a positive x squared plus 1. And I would point out that this is not equal to f of x. So then we ask, is it odd? Does f of negative x equal negative f of x? And this is where I want everyone to be super duper careful, because I've seen this mistake from a lot of people. So I just want to be super extra clear about what's happening here. So I've already found f of negative x. It's negative x cubed over x to the 6 plus x squared plus 1. If I look at negative f of x, which is just negative x cubed over x to the 6 plus x squared plus 1. What I want everyone to know is that if you have a negative of a fraction, you don't multiply the top and the bottom by the -1. It is either the top or the bottom, but not both. Because if you multiply the top and the bottom by -1, you're really multiplying by -1 over -1, which is like multiplying by +1. So the way you can do this, if you want to be like super, like I think you can just say, great, this is negative x cubed over x to the 6 plus x squared plus 1. Check. But if you want to show a little more work because you don't feel so great about that, you can say, well, this negative out here is really a -1 times your stuff, which is really -1 over 1 times your stuff. And then when you multiply fractions by fractions, it's always the top times the top, which is going to be negative x cubed, over the bottom times the bottom, which is going to be 1 times all that stuff is just all that stuff. So if you really want to see why, when you multiply by -1, it's either the top or the bottom, you multiply by -1, that's why. Because your -1 is a fraction is either -1 over 1 or 1 over -1. So that's what's going on there. In either event, we have seen that negative f of x is equal to f of negative x, right? This and this are the same. So yes, it's odd because f of negative x is equal to negative f of x. Cool. Let's look at the last one here. F of x equal to x to the 5th plus x squared. So just as a point, just as a teacher kind of point, something to be aware of, like if there, I probably wouldn't ask 3 of these questions on the test, but if I did, it would probably be not unreasonable to expect one of them to be even and one of them to be odd and one of them to be neither. That's kind of like not like, if you think about like how teachers think about writing tests, like they're usually trying to cover the breadth of topics. So if you see a number of questions, like for example, when you take calculus next quarter and you start talking about continuity and your teacher asks you like, is this function continuous or discontinuous at this point and at this point, it's probably going to be continuous at one of the points and discontinuous at another point for the same sort of reason, because we're trying to get you to see all the things. So I'm expecting this one to be neither. Let's find out. So first, is it even? We still have to check all the other things. So f of negative x is equal to negative x to the 5th plus negative x squared, which is negative x to the 5th plus x squared, which is not the function we started with. So it's not even. No. Is it odd? So then we check what negative f of x is, and negative f of x is negative x to the 5th plus x squared, which is negative x to the 5th minus x squared. And that is not equal to f of negative x, which was just what we had right there, right? Those aren't the same. So is it odd? No. And if it's not even and it's not odd, then we say it's neither. So f of x is neither, or neither, however you want to say it, even nor odd. You can just say neither, though. You don't have to write out all those words. Okay. Let's look at question D. Sorry, question 8, not question D. 8. Let me give myself a new piece of paper here. I need more paper. And then you all should think about which of the questions from problem 2 you would like me to graph. I will just graph whichever ones I think are the most important, but if there's one specifically you want to see graphed, let me know. So for 8a, let's see, we're being asked to first find the inverse function and then use it to find the range. So f of x is equal to 2x minus 3 over 4x. We're being asked to find the range of this function. As a side note, we know the domain of this function is everything except for 0. So if we were finding the domain, just to point out, we would say, oh, we want 4x to be, we want to really exclude where 4x is equal to 0, which is where x is equal to 0. So the domain, not that we're being asked for it, would be negative infinity to 0, union 0 to infinity, because it would be everything except for good old 0. Okay. But now the range, we're going to find the inverse function first. So step 1, write it as y equal to 2x minus 3 over 4x. Step 2, switch them all up. So x equals 2y minus 3 over 4y. Now we're going to solve for y. And this one's a little extra special because there are multiple y's. So we have to be more careful when we try and solve for y here. So I'm going to multiply both sides by 4y. So 4yx equals 2y minus 3. And then if you have multiple y's, you have to bring them all to the same side. So I'm going to have 4yx minus 2y equals negative 3. The reason we bring them all to the same side is so that we can factor it out. So factor out the y. You're left with the 4x minus 2. And then finally, divide both sides by whatever y is multiplied by. So divide both sides by 4x minus 2. So we end up getting y equal to negative 3 over 4x minus 2. Or f inverse of x is equal to negative 3 over 4x minus 2. And now we want to find the domain of this. So the domain of f inverse, well, it's the same sort of idea as up here. We're still seeing we have a fraction. We want to exclude where the denominator is 0. So we're going to exclude 4x minus 2 equal to 0, meaning 4x equal to 2, meaning x equal to 2/4, which is 1/2, or 0.5 if you like a decimal. So I want everything except for 1/2. Everything else is good. I don't want to put 0 on this number line here. 0 is not important here unless it's actually the point I'm caring about. The only things that are going on my number line are the points that I actually care about. So my domain of f inverse, aka the range of your original function, is exactly this, everything except for 1/2. It's kind of neat. If you wanted to, not that we should spend our time doing this, but if you wanted to, you could set this function equal to 1/2 and then show that there's actually no solutions, which is kind of cool. But we're not going to do that because we don't need to do that. So let's look at the last question here, and then we'll circle back around to whatever graphing we can get to. So let's see, if we look at 8b, same question. For f of x equal to log base 2 of x plus 4 minus 3. So for a logarithmic function, we should just kind of know, although we're still going to do the work because we've been asked to do the work, right? The problem says to find the inverse function. That's part of doing it. But we know that for a logarithmic function, the range should be everything. Well, let's find the inverse function. So y equals log base 2 of x plus 4 minus 3. X equals log base 2 of y plus 4 minus 3. X plus 3 equals log base 2 of y plus 4. 2 raised to the x plus 3 power is equal to y plus 4. So 2 raised to the x plus 3 power minus 4 is equal to y. So my inverse function here is 2 to the x plus 3 minus 4. And the domain of the inverse function, well, there's no restrictions. There's no fractions. There's no square roots. There's no logarithms. So the domain of this function is everything, which means the range of the original function is everything, which we already kind of knew, but good to think about it in this way. Okay. So let's look at some graphing stuff. And I'm gonna select the ones I think are probably the best. Not the best, but the ones that might cause you to be the most interesting. So let's look at something like, let's actually look at h. So this is 2h. So graphing f of x equal to x to the 4th times x minus 2 times x minus 5. It's kind of funny. So I want to graph this. So step 1, I don't know, step 1. First thing I'm going to do is find the y-intercept. So if I set x equal to 0, y is going to be f of 0, which is 0 to the 4th times, it doesn't matter after that. 0 times anything is 0. And I definitely encourage you not to show extra work there. You don't need to. Once you see it's 0, just say it's 0. X-intercepts, on the other hand, are a little bit more work. I'm setting x to the 4th times x minus 2 times x minus 5 equal to 0. And I'm going to get x equal to 0 with a multiplicity of 4, meaning we're going to bounce. I'm going to get x equal to 2 with a multiplicity of 1, meaning we're going to cross. I'm going to get x equal to 5 with a multiplicity of 1, meaning we're also going to cross. Now that's really kind of all the information I've got. So I'm going to draw my little thing here. And I've got 0 and 2 and 5. Oh, I forgot about the end behavior. I know I was forgetting something. So you could, well, no, you should find the end behavior. So the degree of this polynomial is 6. You can either think of multiplying it out, or you could literally add up the multiplicities. The multiplicities should always add up to the degree, which is kind of neat. And then my leading coefficient, so if we look here, there's no negative signs in front of any x's, so the leading coefficient has to be positive. It'd be positive 1. So these two pieces combined together means our end behavior is looking like up on the left, up on the right. So we're going to start up here on the left. We're going to come down towards this. We're going to bounce there, cross there, cross there. So I'm going to bounce and then cross, and then cross. It doesn't have to be perfect. It's not going to be perfect, but like, because I don't know how high this goes or how low this goes, but it should look relatively smooth. It shouldn't cross like over itself, meaning like I shouldn't like circle back around that way or something wild like that. It should definitely pass the vertical line test, meaning any vertical line should only cross through one point at the most. Yeah. Let's look at J. See, if you have a request, you're certainly welcome to say it, but I don't see any requests. I'm going to go with 2J. So 2J is the function x squared minus 4x plus 4 divided by x squared minus 2x plus 1. Which is kind of, well, it's fine. So all the things, y-intercept, f of 0 is equal to 0 minus 0 plus 4 over 0 minus 0 plus 1, which is 4. And remind you, the y things are easiest to find if it's written like this, whereas the x things are easiest to find if you factor it. And we should have factored it to make sure there weren't any holes. So this factors as the top is x minus 2 times x minus 2. The bottom is x minus 1 times x minus 1. So now if I want to find the x-intercepts, I'm going to set the top equal to 0, which means I'm going to get x equal to 2 with a multiplicity of 2, meaning we're going to bounce. For the vertical asymptote, which is also an x thing, correct? Because vertical asymptotes are x equal to whatever the number is. We're going to set the denominator equal to 0. Again, much easier to set the factored form equal to 0. So we're going to set x minus 1 squared equal to 0. We're going to get x equal to 1. A vertical asymptote should be wherever the function is undefined. I will also point, well, okay, we only get vertical asymptotes where functions are undefined, but that's not always what happens. But generally, that's the case. You can, although you don't have to, I would point out here that the multiplicity of this asymptote is also 2. And so here you get bouncing within its intercept. When it's an asymptote, that just means either both sides go up or both sides go down. Whenever your asymptote has whenever your vertical asymptote has even multiplicity, they're both going the same direction, either both up or both down. And then finally, the horizontal asymptote, we look at the unfactored form and we see, oh, the degrees are the same. So the horizontal asymptote is the quotient of these leading coefficients, which haven't been written, but they're both 1. So the horizontal asymptote is y equal to 1 over 1, which is just y equal to 1. And then we put it all together. So let's see here. I've got a y-intercept of positive 4, an x-intercept of positive 2, a vertical asymptote at 1. Oops, 1, sure. Okay, yeah, good job. And a horizontal asymptote at 1 as well. And then I'm going to start at my y-intercept and say, well, if I go towards the right, I have to go upwards because I can't go downwards and cross this x-axis without an x-intercept. And then on the other side of this, we know that it has to be going the same direction because the vertical asymptote had an even multiplicity. So we also have to be going up this way, which means we're then going to come down, we're going to cross the horizontal asymptote, and then we're going to bounce off our x-intercept. And then we have to get closer and closer and closer to this horizontal asymptote as we go out to the right. On the left-hand side, the only thing that is to the left, the only feature that we have to worry about to the left is the horizontal asymptote. So we're just going to go like that. And that's it. I mean, that's not it. There's still more questions here, but that is as much time as we have. Yeah, that's all we got. So as far as the exam goes, I am in the middle of writing it. So I will try to get it written as quickly as possible. I intend to have it posted no later than 2 p.m. I will certainly post an announcement when it is up and available so that you can start working on it as soon as you're ready to. It should be very similar as far as the mechanics of it should all be very much the same as they were for the first exam. So if that went fine, then this should also go fine. I will be available over the weekend via email. Again, you know me, I'm not up in the middle of the night, so I would encourage you not to take the exam in the middle of the night if you anticipate maybe having issues, but I don't think anyone should have any issues, so please feel free to take it whenever works best for you. All right. Yeah, I'll see you all next week on Monday. Take care. Thanks for accommodating this virtual experience. Sorry to have to change things up at the last minute, but I think it worked out for everyone. And if you missed, well, I guess I should say, I'll post the video up on Canvas as well, so that for the people that didn't make it in, they can watch it or not. All right. Take care. I'll see you all later. You too. Have a good weekend as well. Although harder to when you're taking an exam, but yeah. Have a good weekend.